This is Mr. Lee's physics class. I'm Mr. Lee. By now, we have discussed what the internal energy of a body is. It is the sum of the kinetic energy and the potential energy of all particles in the body. This time, I will introduce to you a type of energy transfer called heat. You have learned in mechanics that energy can be transferred through doing work, usually represented by the capital letter W in calculations. It basically involves exerting a force over a displacement. But this is not our focus today. Here we focus on another type of energy transfer called heat, usually denoted by the capital letter Q in calculations. It is a transfer of energy within a body or from one body to another due to a temperature difference. And the direction of such an energy transfer called heat is always from a higher temperature region to a lower temperature region. So once again, both work and heat refer to the energy transfer, but work is due to a force exerted over a displacement, while heat is due to a temperature difference. As they are both energy transfer, they both bear the units of energy, Joule, written as capital letter J in short. You probably have heard of the term heat energy before, either when you learn elementary science or from other sources. But it's actually wrong to speak of the term heat energy. The thing is, formally heat is not an energy but only a transfer of energy. Say, now you put a red-hot piece of iron into a tank of cold water. According to here, that heat is the transfer of energy from a higher temperature region to a lower temperature region. It is correct to say that there is a heat transferred from the higher temperature iron to the lower temperature water. But it's incorrect to say that the iron has more heat energy than the water, simply because heat is not a type of energy but just a transfer of energy. If you're really to compare the energy possessed by the hotter iron and the cooler water, the only thing you can say is that the average kinetic energy of the particles in the hotter iron is higher than that in the cooler water because temperature is a measure of the average kinetic energy of the particles in a body. Now, let's see how the term heat is correctly used. Using this again as an example, you can speak of things like heat transfer, heat gain, heat loss, or heat release as they all bear the meaning of energy transfer of some sort. For example, you can say a heat transfer of 10,000 joule from the red-hot piece of iron to the water. This just means that 10,000 joule of energy is transferred from the hot iron to the cold water due to their temperature difference, or due to that the iron is at a higher temperature than the water. This is a slightly better way to say it because it more precisely explains the direction of the heat transfer, always from a higher temperature object to a lower temperature object, in this case from the hotter iron to the colder water. You may also say that the heat gain is 10,000 joule for the water. It just means that 10,000 joule of energy is transferred into the water or gained by the water due to a temperature difference. Similarly, you can speak of heat loss or heat release of 10,000 joule from the hot iron. It just means that 10,000 joule of energy is transferred away from the iron or lost by the iron or released by the iron to the water, due to a temperature difference, of course. The term heat can also be used as a verb. This way of using the term is also consistent with how we have been using it in our daily life. Like this, the water is heated up by the iron. This way it just means that energy is transferred from the hotter iron to the colder water due to that the iron is at a higher temperature than the water. Other similar way to use the term heat correctly are: heat is transferred from the iron to the water, or heat flows from the iron to the water. These sentences all basically means the same thing. Now, let's go into more details of this example. As heat means an energy transfer, and such a transfer is from the higher temperature iron to the lower temperature water, it implies that the iron is losing energy while the water is gaining energy. From common sense, you also know that the water is going to become warmer while the iron will cool. So, can we explain these temperature changes from the point of view of heat flow? Since now the iron is losing energy from within, its internal energy must decrease. Now, take a look at this expression of the internal energy of the iron. By the way, a quick refresher here. This term, the average potential energy of the particles, usually depends almost only on the state of the body, and this term, the average kinetic energy of the particles, relates only to the temperature of the body. Since the iron is in solid state throughout, the average PE of the particles stay unchanged. And of course, the number of iron particles also remains unchanged. So, a loss of internal energy must be a result of a decrease in the average kinetic energy of the iron particles. This implies that its temperature decreases as its temperature is a measure of the average kinetic energy of its particles, which, as I just said, has decreased. Then what about the water? As heat flows from the iron to the water is gaining energy. Again, based on this expression of internal energy, and assume that the water does not change its state, that is, no turning into water vapor through boiling or evaporation, there is no change in the average PE of water particles, as this depends almost only on the state. Also, there is no change in the number of water particles. So now, an increase in internal energy can only result from an increase of the average kinetic energy of the water particles. This means that the temperature of the water must increase. So, the conclusion is that if a body has a net heat loss, its temperature drops. And if a body has a net heat gain, its temperature rises, provided that there is no change of state happening in the process, very much like the one shown here. The case with change of state will be discussed later. But an important question is, what happens then? Does the water go on to gain heat forever and its temperature becomes infinitely high and the iron also keep losing heat forever in a similar fashion? Of course, this is impossible. Before answering this question, let's try to understand on what factor and how the rate of heat transfer depends. We will not discuss all these factors but just one, the temperature difference, also written as delta T mathematically. As we discussed, heat flows due to temperature difference, so it makes sense that the greater the temperature difference, the higher the rate of heat transfer, or simply put, the faster the heat is transferred. And the smaller the temperature difference, the more slowly the heat is transferred. And when the temperature difference is no more, heat also ceases to flow anymore. With this in mind, let's try to sketch how the temperatures of the iron and the water change with time. At the beginning, their temperatures differ a lot and so the heat flows fast from the iron to the water. Therefore, the temperature of the iron drops fast and similarly that of the water rises fast. But as their temperature difference gets smaller, heat flows also becomes slower due to this fact just mentioned, that the smaller the temperature difference, the more slowly the heat flows. This way, the temperature of the iron will also drop not as fast compared to before, and that of the water will rise also not as fast as before. This cycle goes on. So, the temperature of the iron keeps dropping but drops more and more slowly, and the temperature of the water keeps rising but rises more and more slowly. Ultimately, their temperatures approach the same value. And then according to this point earlier mentioned, heat stops to flow anymore between the iron and the water. Then they are said to achieve thermal equilibrium. This word just means that the two objects finally has the same temperature and so no heat flows between them anymore. If we neglect the heat transfer to the surrounding but focus only on that between the iron and water, the situation will be no temperature difference, then no more heat flow, no heat flow, then no further temperature change, and their temperatures will go on to be the same. Of course, in reality, this is not exactly true because there can still be a temperature difference between this system of iron and water and the surrounding. Say, if this entire system is warmer than the surrounding, then heat flows from the system to the surrounding and then the temperature of this system drops due to such a heat loss.